This is the first of 4 videos that I've made for solving trigonometric equations. As you're going through this video, keep in mind that there are 5 steps for solving a trig equation. I'd recommend that you write these down and follow along as we go through each of the videos. The first step is to isolate the trig function. Once you've done that, you can solve for the mess or the argument that's inside of your trig function using the unit circle. Usually this will give you 2 solutions, but sometimes you'll only get 1. From there you can add any number of full periods to get a formula from which you can solve for the variable that's inside of your mess or your argument. Sometimes you're going to be asked to find a solution set that's on a given interval, for instance 0 to 2 pi. And as you go through these videos, I've indicated here which of these steps are highlighted in each of the videos 1 through 4, and they get a little bit more difficult as you go through from videos 1 through 3. And finally, in video 4, we're only going to focus on how you isolate the trig function when your equation is kind of complicated. So the first problem I want to look at is how you would solve 2 times the sine of 2x minus the square root of 3 is equal to 0. And first thing that you want to do again is to isolate the trig function. So I have the sine of 2x, and to isolate this I will add the square root of 3 and then divide by 2. So I'll get square root of 3 divided by 2. From here I want to somehow figure out what the argument is, where the argument is 2x. And the way I want to think about this is just to think of 2x as a great big angle. So it's kind of messy, it's 2x, it's not just simply theta, but I can still solve for it. And one of the ways that people like to do this is to use the inverse sine on both sides, and you'll end up with the inverse sine of the square root of 3 over 2. So if you do this, one of the things you have to remember is that the inverse sine was defined using a domain restriction on the sine function, where you're only going to look from minus pi over 2 to pi over 2. So over here on my graphing calculator, this is the sine of x, this is the square root of 3 over 2, and this is the only angle that's going to come out of this formula. So I'll get 2x is equal to, in this case that will be pi over 3. Is equal to pi over 3. And that's great, but the problem is that I'm missing all of these other solutions here, and I have to think about how I can get those. So usually, instead of looking at the inverse sine, I don't like to do this guy, so forget this. I will typically just go to the unit circle and think about what this statement means. So when I have the sine of theta, I want to remember that that's a y-coordinate, and I know that my y-coordinate here is the square root of 3 over 2. I'll look on the unit circle, square root of 3 over 2 is maybe right about here, and that's going to correspond to not 1 but 2 angles. First one is here, that was pi over 3, we already had that one, and the second angle is 2 pi over 3. So if I look at the unit circle, I get 2 solutions, one for the angle pi over 3, one for 2 pi over 3, and that corresponds to this guy that we just got from the inverse sine, and also this guy over here. So this is really all the information I can get off the unit circle. I've isolated the trig function, I've solved for a mess equal to some angles, in this case I got 2, and my next big step is I need to think about this idea of period. The idea of period is that when I'm sitting at pi over 3, I have a y-coordinate of the square root of 3 over 2. But if I went around the circle one full revolution, meaning if I added 2 pi to pi over 3, I'll end up at the same place and I'll have the same y-coordinate. I could add 2 pi again and again and again, and I'll always get that same y-coordinate. So when I look at 2x equal to pi over 3, I have to remember that I could add any number k of full revolutions 2 pi to my solution. Likewise, if I'm at 2 pi over 3, I could go around this unit circle any number of times, always end up at the same location with the same y-coordinate. So again, I could add any number of full revolutions. So I'll have plus 2 pi k. Next big step that I want to think about here is that I've solved so far only for this guy theta, 2x. But what I really want is to know what x is equal to. So I need to solve each of these equations here and here for x, and in this case what I need to do is to divide both sides by 2. I should say all sides since I have multiple equations. So I'll divide everything by 2. Pi over 3 divided by 2 is pi over 6. 2 pi k divided by 2 is 1 pi k, or just pi k. And for my next equation, 2 pi over 3 divided by 2 is 2 pi over 6, or pi over 3, plus 2 pi k divided by 2 is pi k. And at this point I've solved for x. I have a formula. There's two different formulas that I need to use, and that will describe the complete solution set for my trigonometric equation.